What's going on in the chat here? All right, ladies and or gentlemen, strong or on the gentleman portion. Welcome back to your favorite class. Yes. What is the chat today? Alex is stirring up a bunch of controversy. We got like gorillas kissing each other and minions. What is happening? This is like just falling apart. Right. Welcome back. Couple of announcements. Homework 6 was due today. I'm putting together homework 7. I didn't quite finish. I was a little too busy grading your manufacturing documents, I guess. But I did grade all the manufacturing documents. So if you submitted one, or you think you submitted one and you didn't get it back, suspicious. Okay, email me and let me know. Homework 7 is going to come, and I'm just going to say that it's going to be ungraded. So I'll submit it, or I'll send it to you guys, and I'll also release the solution with it, so you can just kind of like work through that maybe on your own time and give it a go. Okay. I'm also going to make a study guide for the final exam, just like I did for the first exam, so you have that. The final exam, since it's like a 2-hour form, there's going to be a lot more sort of workout questions than there were on the first test, because we just have a lot more time, and honestly, there's a lot of calculation that needs to be done in composites class. So going to have a little bit more long form calculation on the final. Just for your information, I posted the time for the final. Here it's going to be Thursday, so it's 2 weeks from today, via Teams from 2 to 4 p.m. Okay, so there you go with that. It'll be similar format, kind of open everything. I'll post the test online once the time hits, and you'll have 2 hours to do it and submit it to me. Okay, so that's that. Right. Any questions? Besides, why does Alex Ramiar look like a snowman in Peter Griffith's living room? Who knows? Okay. I always liked that Family Guy episode where Peter and Brian are building a house and they have walkie-talkies, and you know, who is it? Brian insists that Stewie keeps saying over or something like that at the end of his conversation, and Brian says something like, "This conversation is over," and Stewie says, "This conversation is what? Over?" And he says that over and over and over. It's just really funny scene. But anyway, Family Guy, good things. Okay, let's get on with the lecture. Family Guy, hilarious. I just want to bring up one thing quickly from the end of last lecture. So this is the very last slide of the unidirectional lamina fin failure theories. Here's a general strategy for attacking the failure theories, and there's an example problem here. I'm going to do this example problem in YouTube, maybe make a 10-minute video to kind of go over this particular example, and submit that to you guys, probably release it tomorrow. You can take a look at that. I want to get on to laminate theory because we need like a solid week to do it. All right, so let's get on with laminate theory, which is the next set of notes, which I did post on Blackboard. And that's what we're going to start on today. It's laminate theory. All right, so let's move on that. All right, so away we go. New set of notes, laminate theory. Why is my pen not working? What is happening? My pen is out of ink. The old turn it off, turn it back on trick. I bet that's going to work. Yep, that worked. Always works. Turn it off, turn it back on. Okay, so away we go. New notes. This is laminate theory. All right. So the first thing we should maybe do is sort of define a laminate, what it is, and some of the basic theory behind. Okay, so up to now, we've really talked about thin unidirectional composites. And when we talk about a single thin unidirectional layer, that is like one layer inside of what could be a multi-layer laminate. So typically for the vocabulary here, one layer of thin unidirectional material we will typically call a lamina. All right, I've kind of like thrown that word around a little bit without fully defining it, but now it's on the books, baby. All right. Many lamina that are stacked on top of each other consist of a laminate. So a laminate is many stacked lamina. Okay, and I'm kind of trying to show this with a picture in the notes. Is this like introduction slide number 2 in the notes? Is this idea here. And so sort of a picture of this. And I bring in the picture from the notes because, again, my artistic skill is very suspicious. But here is something like this. All right. So basically everything we've done to this point is on this sort of lamina structure. We talked about how to get properties of that lamina, like in the direction of the fibers, across the fibers, and in some general arbitrary direction. We talked about what the failure strength of this lamina is, in the direction of the fibers, across the fibers, in some arbitrary direction. Okay. The next step in our analysis of composites is what happens when we stack many of these lamina on top of each other to create a laminate. Okay. And your laminate can consist of many layers that are not necessarily all with the fibers in the same direction. You could have fibers that run in multiple directions, and that's what we're kind of trying to show with this particular picture here. So in this particular picture, this bottom layer, the fibers are kind of like running in this direction. The next layer above from that, the fibers are kind of like running in this direction. The layer above that, the fibers are running in this direction. And this layer here, the fibers are running in this direction. Okay, so what we need to do is we need to come up with a method for describing like what is the stiffness in like some arbitrary direction of that laminate. All right, what is the strength, some arbitrary direction of that laminate. Strength theory is a little complicated, but what we want to do is describe basically sort of the mechanical engineering properties. So we want some sort of like engineering properties of this laminate. Given the constituents inside of the matrix. So that's like, what's the strength of the fiber? What's the strength of the matrix? We're going to want this based on volume fraction, obviously. The lamina orientation, or what we call the stacking sequence, will become important. And finally, the overall thickness is going to be important. Okay. So that's what we're going to be doing over the next basically like 4 lectures, is really trying to derive what is like the stiffness of this material. If we apply some force, if we apply some moment, how's it going to bend? How's it going to elongate, deform, etc.? Can we get some like stiffness parameters or sort of understand what the stresses are in each one of these layers as we go through? Okay, so let's get into some like basics about laminates, because we need to just lay down some very basic ideas of what's happening in the laminate so that we can have some discussion. All right, so laminate is created by stacking multiple lamina. Kind of already wrote this. But we can drive it home. All right. By convention, we sort of assign the very bottom layer as layer number 1. And we're going up to layer N. Okay. So N is just like a number, where N is the number of lamina in your laminates. Okay. When we're talking about a single lamina inside of our laminate, we'll generally use the convention that we're talking about the case lamina. Okay. So layer of interest is the case lamina or layer. So I might say things like, what is the stress in layer K? What is the strain in layer K? All right. When we have a laminate, we place a global XYZ coordinate system at the midplane of the laminate thickness. So global XYZ coordinate system placed at midplane of laminate stack. Okay, and we always say that the Z direction is the sort of out of plane direction. So the Z direction's out of plane. Okay, then each layer that exists inside of that laminate has its fibers running in a direction that is oriented in some way with the XYZ coordinate system. Okay, so the XYZ coordinate system is sort of global for the laminate, and you sort of define it. And then each individual layer inside of that laminate has an orientation with respect to the global coordinate system. Okay, so each layer has fibers which run at an angle with respect to the global X, Y, Z coordinate system given by theta K. It's the angle that your fibers make with the global XYZ coordinate system. Okay. So let's sort of draw like a side view of what a laminate might actually look like. Okay, so I'm stacking multiple layers on top of each other. And so let's say I'm making a, I don't know, 8-layer laminate. All right. So segregate this in half, segregate this in half, segregate this in half, and each one of those goes in half. Okay, so this gives me an 8-layer laminate. So here, n equals 8. Okay, 8 layers. I'm going to put my global XYZ coordinate system emanating at the midplane. So my XYZ coordinate system, I'm going to be looking at just one side of this laminate. So here, this is like X, Y would be into the page, and Z is your through thickness direction. So that's where my XYZ coordinate system sort of emanates. Okay. Each one of these layers has a number. This is layer number 1. It's on the bottom. So here, this is layer 1. And so we'll say that for this particular layer, K is equal to 1. The kth layer, K is equal to 1. This is the first layer. And obviously, this very top layer, K is equal to N, which here is equal to 8. Okay. Last thing that I want to say is that we're going to assign a variable here that denotes where the bottom of the lamina is. And so we'll say here that the bottom of layer K is at ZK. Bottom of layer K is at location Z sub K. Right. So this distance here would be Z sub 3. Okay, it's the bottom of the third layer. That location is Z sub 3. this location here would be Z sub 7. Okay. Just as an example, the bottom of the 7th layer. That's because we don't want any zero index, right? Z1 is the bottom of layer 1, Z2 is the bottom of layer 2, so on and so forth. Okay. All the way up to Z8 for my Z7 up to Z8 for the top of my 8th sort of layer. Okay. Okay. Yep, that's right. All right, so there we go. We got some basic semantics down for how we're sort of organizing the coordinate system and talking about our individual layers. Now, what we want to do now is talk about the laminate stacking sequence and really sort of hammer that idea home, because that'll be important as we move forward. Next. Laminate stacking sequence. Oh, handwriting today. Just too much coffee. I was trying to like stay awake grading your papers. All right, your laminate stacking sequence. So when you go to create a composite laminate, you want some sort of method to sort of describe how you're doing the layup in like a shorthand way. All right. So if I'm going to make a laminate and stack 16 layers on top of each other, I don't, I need some fast way to tell you, if you're going to be manufacturing it for me, how I want you to stack those layers on top of each other. All right. So I need an easy way to sort of describe that. And so the stacking sequence is what is sort of trying to achieve that. Okay. And so the stacking sequence is like a series of numbers that describes how the various layers are stacked on top of each other to make your composite. Okay. So this is a series of numbers which describes the orientation of the various layers in the laminate with respect to the global XYZ coordinate system. Okay. And when we do this, the first value in the stacking sequence is the bottom layer. Okay. So best illustrated sort of with an example. So one example might be as if I want an 8-layer laminate where every single layer has the fibers running in the same direction. All fibers in same direction. Okay. What would that look like? Well, that would be like if I did this following situation. So here, this is like what's going to be the top layer. Then the next with the fibers running this way. Then the next with the fibers running this way. 8 total. Okay. These are all going to be stacked on top of each other to make my composite. So if my global XYZ coordinate system was something like what I would expect, then this particular layer has its fibers running. Let's do it the other way. Let's do it this way. then this particular layer has its fibers running in a 0-degree orientation. These fibers run in the same direction as this x-axis, right? Same thing with the layer below it. Those fibers run in that x-axis, okay? So this would be a 0-degree layer, this would be a 0-degree layer, this would be a 0-degree layer, and all of the ones that would create for me an 8-layer composite would all have this orientation of 0 degrees. So the stacking sequence is the following: 0, 0, 0, 0, 0, 0, 0, 0. That's your stacking sequence. Pretty straightforward, okay? A lot of zeros. You guys are used to that, right? No, just kidding. You guys do all your homeworks. Some of you, I don't know, a little suspicious. I don't want to write all those zeros. That's kind of annoying. So in shorthand, this is typically seen as the following. 0, 8. Okay, that's 8 layers of 0-degree orientation lamina laid on top of each other. Right? Now mean. All right, let's do one more example. We may wish to create a laminate that has sort of an equal distribution of layers pointed in various ways. This would create for us sort of what we call a quasi-isotropic structure. And let's say that that stacking sequence was 0, 90, 45, minus 45, minus 45, 45, 90, 0. Let's say that that was one particular structure that we had. The idea here is that I lay one down 0 degrees, then another one 90 degrees to that, then another one 45 degrees, another one minus 45 degrees, minus 45, 45, 90, 0. Okay? That's the general idea. This would be another 8-layer structure, but it has a different stacking sequence, so you get sort of 2 different kind of ideas. All right? I'm not going to try to draw that one. There's actually a picture of this in the notes, and I'm just going to bring in both the pictures here so that you can kind of just see this. It's a little bit better from the notes. Okay, so here's an example of the 2 different laminates that I was just talking about. Here's your unidirectional layup. Here's your quasi-isotropic layup. Okay, and so the coordinate system here for this would be something like X, Y, Z. That would generally be your global coordinate system. And we see each one of the composites in the unidirectional have them all in sort of this 0-degree orientation. And then we say for the quasi-isotropic, start with the bottom, 0, 90, plus 45, minus 45, minus 45, plus 45, 90, 0. Okay, so that's how we define our stacking sequence for our particular laminate. Always starting with this as your first layer. Okay. Again, this is kind of a 8-layer laminate, and I might want to write this in shorthand. And we have a method for that. And that would be the following: 0, 90, 45, minus 45. Close it off with a little s on the bottom for symmetric. Okay. So basically, when you have a symmetric laminate, you do those 4 layers, and then you mirror that about the last layer. So remember, this is like layer 1, 2, 3, 4, then 5, 6, 7, 8, if it were symmetric. Okay, now that we got some nomenclature out of the way, let's do some math. And I'm going to bring in a figure here that will become the Bible of our derivation over the next probably 3 lectures. And I'm going to give you some time to copy this figure because this figure will actually be somewhat important for what we're going to do. Okay, so here you go. Important figure. And instead of trying to draw this for myself, which we all know is a bit suspicious, I'm just going to bring in the figure here and hope that you can sort of do your best to copy this down. And I'm going to talk about this figure and how we're going to use this in our derivation. Okay, so here's this figure. I'll maybe give you a couple minutes here, but I'll sort of talk about this as you're maybe copying it down. Again, we see our global coordinate system, this X, Y, Z. And we notice here that the XY plane is in the center of the laminate stack. Okay. So here's this XYZ coordinate system. All right, the XY plane is in the middle of that stack. What we want to do with the upcoming derivation is assume that this here is like an undeformed, and we're moving to a deformed condition. And I want to investigate how an arbitrary point in the center of that laminate, this point B, how does the strain develop as we move from the undeformed condition, point B, to the deformed condition, B prime? Okay, so here, how does strain develop as I move from B to B prime? I'll give you a couple minutes to do your best with that figure. Really encourage you to copy that down right now. Jeez, the memes. I only have 3 pages left in my notebook. Time to get a new notebook. Alex, do you have like a party going on in your house? Like, what is going on, man? It's like the strobe snowman. Oh, it's a chicken. I thought it was a snowman. At least he's wearing a mask. But I thought chicken's gonna get the corona. Anything, really? All animals can get it? Wow. Seriously? Dang. It went into animals, and apparently the animals are getting it. In Danish land? In Danish land. It's the Netherlands, right? Or Denmark. Is it the Netherlands or Denmark? Are they one and the same? Hey, stop it with the spotlight. Copy down the figure. Better keep Rocky safe, no doubt. Rocky's at daycare right now, so maybe he's getting it from the other animals. Huh, they can be carriers, but they can't get sick. Interesting. Does that mean that I could get it from an animal? Or do I have to get it from a human? Well, yeah, it evolved from bats, I guess, but crazy. Guess my dog better not cough on me. Got to start putting a mask on Rocky. Okay, so here's the general strategy, okay? So we're going to start with this sort of like general laminate. And notice that we haven't drawn any layers in there. We're just kind of like talking about sort of like a generic plate, all right? The first thing I want to do is, since I know this plate is all sort of like deforming in the same way, regardless of how many layers I have, we're going to assume that all those layers are sort of like moving and straining together. And so all the layers will have the same strain. Okay. So here's the strategy. Of the upcoming derivation. One, we're going to start with this general plate and sort of define the strain at this arbitrary point. As I mentioned, that's going to be point B. As we go from B to B prime, what is the strain that develops? Remember, strain is like the deformed length divided by the original length, right? Once we have that strain, we can say that that strain is developed in some sort of variation through the thickness of the laminate. So we assume the strain is continuous through laminate. Okay. And that will allow us can determine stress in layer K. Okay. With, for example, if we have epsilon x, epsilon y, gamma xy, which we're going to derive, giving our little plate theory. Sorry, we want the stresses. So we can calculate the stresses, assuming we have some sort of stiffness, Q, of layer K, multiplied by the strains that we develop in layer K. That's the general concept. So the stresses that develop in layer K is just the stiffness of layer K, which we know, multiplied by the strains that are in layer K. Okay? K. K. Right? Then we're going to add up all of the stresses that are inside all of the layers in one particular edge of the laminate and say that the total area of that edge multiplied by the stresses in each one of those layers has to be equal to the original force that we put on the laminate in that direction. Okay, so that's the general idea of the next piece. Okay, then add stresses from all layers together. and multiply by laminate cross-sectional area and enforce equilibrium such that, in shorthand, the stresses that are developed multiplied by the area of that cross-section is equal to whatever force is on that particular side of the laminate. Right? We're trying to balance like the stresses that are inside the laminate with whatever forces we applied to the laminate. Sort of makes sense. It's equilibrium, right? But because we have different orientations of the fibers in different directions, the stresses inside of each one of those individual layers will not be equal. Okay. So we need to sort of like calculate what's the stress in this layer, what's the stress in this layer, what's the stress in this layer, multiplied by the area of that cross section. That has to be balanced with the force that we apply. I mean, this is just like a very basic sort of shorthand idea. All right. And finally, relate those applied loads. So here's your applied load. Back to strains to develop a laminate stiffness. Okay. So generally, I want to know if I apply forces to my laminate and moments to my laminate, what strains are going to result in my laminate. That requires a stiffness matrix that tells me if I have this sort of load, how much does it elongate? If I have a bending moment, how much does it curve? Those sorts of things, okay? And we know for composites that, you know, we can load in this direction and get curvature because of some weird stuff that happens with composites because they're anisotropic in nature, okay? So we have a lot of coupling here that we need to talk about. We have a lot of weird loading situations that lead to weird strains, and we just have to like walk through all that stuff. Okay, so let's talk about what assumptions we're going to make in the derivation, and then probably starting on Monday, we'll go through the derivation. And maybe Monday's the day that you need to wear your math pants. Okay, I thought we were going to get to this math today, but no, wear your math pants on Monday because we got some complicated, you know, Calc 4 level derivations coming. All right. Very exciting stuff. All right. So let's talk about some assumptions we're going to have to make. One, each lamina is thin. We've kind of made this assumption from the very beginning of this like lamina theory, talking about like plane stress in each one of these situations. But yeah, each lamina is thin. This is going to be important in our derivation. And so it's like in plane stress and doesn't carry any shear, more or less, inside that particular plane. All right. We'll say displacements from deformation are small relative to laminate dimensions. Okay, we're going to talk about displacements as like u, v, and w. So u, v, and w, this sort of like displacement vector. All of these values are much, much less than sort of like the thickness of the laminate, which we're going to call h. This is total laminate thickness. Okay, third, strains are continuous through the lamina. Sort of already mentioned this. Okay, it's not constant, it's continuous. Okay, so sort of if I'm like looking at a strain distribution, you know, if you thought about loading this with a typical like bending moment M, something like that, then in your 3005 class, and what we're going to assume here is that the strain distribution through this guy is going to be continuous, right? So hopefully this looks familiar. This would be your strain distribution through the thickness. We are not assuming a continuous stress distribution through the thickness. It's because the different layers are going to be oriented differently, okay? So maybe this layer here has fibers running in this direction, and this layer has fibers running into and out of the plane, okay? In that situation, this layer would be much less stiff than this layer. So you would not have a continuous stress distribution, all right? Just keep that in mind. Next. This one's a little bit difficult to explain, but the displacements vary linearly through the thickness of the matrix, or through the thickness of the laminate. What do I mean by that? Okay, well, if I have a bending moment applied, I'm going to see some deformation that, you know, might look like this. Okay, what I'm saying here is that this line here is linear. Okay, in reality, this does not actually happen. This is probably like assumption. In reality, what actually happens is something that looks a little bit more like that. That's what happens in reality. Ever done this with like a deck of cards? You would see something that looks like this. So we are assuming this. We are not assuming this. We're doing Eulerian plate theory. This is Timoshenko-esque plate theory. For those of you who have really gotten a handle on mechanics. All right, next. Transverse shear is 0. This kind of goes hand in hand with assumption number 1. Okay, so what I mean here is that gamma xz and gamma yz are 0. All right, this kind of comes with your plane stress assumption, but I'm just throwing this out there. In sort of math speak. 6, no plasticity. That one's pretty self-explanatory. Lastly, this one's a little bit tricky to explain, but the vertical displacement is not a function of z. What I mean is that this variable w, which is this vertical displacement that we're going to use, is not a function of z. It doesn't vary through the thickness. If you move up, each point is moving up the same amount. If you move down, each point is moving down the same amount. Okay, it's kind of an assumption that we're making. Again, not realistic, but it's what we're assuming. The last one, it's not listed in your notes, but it is an assumption that we're making, is that all the layers are perfectly bonded to each other. Okay. And that just means that you're not your layers are not sliding across each other like a deck of cards. Okay. Okay, so these are all things that we're gonna use and we're gonna talk about. That's gonna be it for today. Bring your math pants on Monday, baby. I'm telling you. All right. I'll get that study guide posted and I'll get that mock homework posted. Probably by the end of tomorrow. Okay. That's it for today. I'll try to grade your homeworks quickly. So long. See you later, Mr. Chicken Face or whatever.
Rar.
Rar, etc. Exactly.